All right, guys, stat 1150. The purpose of this video is to get into something called the central limit theorem. Easy for you to say. For proportions. It may be a good idea to go back and watch, maybe just think a little bit more about the central limit theorem for means. Maybe not. Maybe you're just ready to jump right in and go for it. So, guys, let's review just a little bit. We're getting into big boy, big girl stuff now. So, our focus is to examine the relationship between samples and populations. Now, if we begin with a population where the value in the population is known and we want to determine the likelihood of getting a particular sample from that population, this is called probability. So the sample is unknown because if we choose it from the larger population at random, we don't know what we're going to get. But the population value must be known for us to determine the probability of getting something from it. The reverse, what we're actually leading up to, is called inference. And inference is a situation where we take a sample. So we go out and collect our sample. So clearly it's known, and we're going to use this information to make an inference about a value that is unknown in your population. Now, the types of problems that we encounter in this class, and again, this is an introductory level class, so we try to keep it simple, believe it or not, is we run into what I call mean problems. Okay? Mean problems, and guys, remember, mean problems, standard deviation goes right along with it. So mean problems, when we're dealing with a sample, the notation we use for a mean and a standard deviation is x bar and sx, while if it comes from a population, the mean and the standard deviation are given as mu and sigma. Guys, the variance is sx squared. The variance is, of course, sigma squared. Now, we're going to get into these new problems called proportions. I'm just going to call it props, okay? It turns out that the notation with a sample proportion is p hat, and a population proportion is just given as p. So, if we are working the probability route, we start with a population proportion that is known, and we can determine the likelihood or the probability of getting a sample proportion, p hat. Here next week, we're going to start more big boy, big girl stuff. We're going to get into inference, where we're going to know our sample because we're going to go out and take it at random, and we're going to use it to make a statement or an estimation of a population proportion that is unknown. So guys, there's this vicious cycle here between probability and inference that I'm trying to make a connection between. Okay, guys, this p hat is something that we can calculate, and it's given as x over n. Now, let me give you an example of this. X is the count, and n is the whole. It's the size of our sample. Again, p hat, it's no brainer. It has to come from a sample. P is your population value. So if I'm interested, for example, in a class of mine, the proportion of students who are female, and let's say I count you guys, and there's 20 students in my class, and there are 11 females. So the top number is the count of whatever I'm estimating, or whatever I'm measuring, and n is the total number, the whole, which in this illustration will be 20. So guys, I could rewrite that as a decimal, 0.55, or I could rewrite that as a percentage at 55%. So p hats can come in one of three different forms, and we have to have the ability, and we got the ability, we've got to know how to interchange these. So if I have 11 out of 20, I know I can change it to a percentage. I also know it can be expressed as a proportion. This simple fact right here is one of the things that drives students crazy, and keeps them from being able to do problems that they're really prepared to do, but they get caught up in the fact that a percentage can be expressed as a fraction or a decimal. So guys, this is important as we move forward. Now, there's what's going on here? First of all, let me just give you the central limit theorem, and then we'll break it down. So the central limit theorem for proportions, and actually that should be for sample proportions, tells us this. If we take, I don't know how I really want to say this. So if we take random samples from a population, and the conditions are met, and I'll talk about the conditions here in just a second. Then the distribution of sample proportions p hat will be approximately normal with a mean of p and a standard deviation of p times 1 minus p over n. Now guys, don't get sloppy here, and this is probably the second thing that people do that leads to incorrect answers, is they get sloppy with this notation, and they'll get sloppy and they'll just do p times 1 minus p over n. Guys, that is not that. When I draw this square root sign all the way down below that n, this entire expression right here is included in. So this is wrong. That will lead to, if you wake up tomorrow and you want to get wrong answers, you're like, you know what, I just think I want to do statistics wrong all day today. Do this. You'll achieve your goal. You will never, ever, ever, ever get the right answer if you do this. That n has to be contained under the square root sign. Otherwise, you're just going to get it wrong. And you go write me an email, Dr. Darber, I don't know what I'm doing. I can't get the right answer. Well, you got sloppy. You know what you're doing. You just got sloppy with something like this. And guys, I'm preaching this because I see it semester after semester after semester. And my goal is to do everything I can to get you to be successful and get this class behind you. So guys, draw that down, and when you put it in your calculator, make sure you do that. All right. Now again, what's P? Well, P is what I told you it was. Back over, P is what? It's the population proportion. What's P hat? It's the sample proportion. Now, what does all this mean? You look at that, if you don't have a really strong background in mathematics, which I'd say most of you don't, because you're still learning, and of course I was there one day too. What does all this tell you? Well, guys, it tells you the same thing that we found out with sample means. Sample mean problems started out this way. We begin with a population where mu and sigma are known. Because guys, if you are starting to work a probability problem, you got to know the population from which you're drawing. You got to. You can't work it if you don't. If I pull out 5 cards and I don't tell you what they are, what's the probability of getting an ace? Well, you don't know because you don't know what you're drawing from. Now, if I tell you that you've got 5 cards over here, and one's an ace, one's a king, one's a 2, one's a 3, and one's a 4, well, you got a 1/5 probability of getting an ace. But if I don't tell you what the cards are, if this isn't known, then you can't determine the likelihood of getting something from it because you don't know the population from which you're drawing. So you begin with a population where these 2 parameters are known. Just safely, as long as the sample size is 25 or bigger, take many random samples. Well, guys, if we're dealing with a sampling distribution of means, then we're going to be taking sample means. Okay? Now, I think I said do this forever. Many, forever. You know, you got the distribution of sample means. The central limit theorem for means x bar tells us that the distribution of sample means will follow a normal distribution with a mean of mu and a standard deviation of sigma divided by the square root of n. That's what the distribution of sample means tells us. But that's not what we're studying now, is it? We're studying the distribution for sample proportions. So how's it change? Well, just as you would think. We begin with the population, yes. But instead of the mean and the standard deviation being given, the population proportion is given. Conditions change. Guys, you got 3 conditions. You got to have randomness and independence. You got to have n times p and n times 1 minus p greater than or equal to 10. I know that looks like a lot, but it's not. And your population has to be greater than or equal to 10 times your sample. If these 3 conditions are met, then you proceed down to taking many random samples. And guys, you don't do this. It's just theoretically there. But instead of taking a sample mean, you take a sample proportion. Instead of taking the second sample mean, you take the second sample proportion. You take another sample proportion, and you end up taking many sample proportions. The central limit theorem for proportions p hat says that the distribution of sample proportions will follow a normal distribution with a mean of p and a standard deviation of the square root of p times 1 minus p all over n, square root of all that. So now how does that help us work a problem? Let's look at an example. I saw the other day in a Gallup poll that there was a report that 38% of Americans believe in ghosts. A random sample of 1,200 Americans is collected. Estimate the probability that 40% or more of the 1,200 believes in ghosts. All right, gang, let's go over here. Begin with the population. P is known. What's P? P is the statement about everyone. P is 0.38. Estimate the probability that 40% or more of the 1,200 believes in ghosts. So guys, ultimately what we've got is we have a distribution of sample proportions P hat that has a mean equal to P, which in this case is 0.38, and has a standard deviation equal to the square root of P times 1 minus P over N, which is the square root of what? 0.38. Now, what's 1 minus 0.38? I can do that in my head, but I've learned in teaching this a billion times not to assume everyone can. So grab your calculator. 1 minus 0.38 is 0.62. What's our sample size? 1,200. All right, so I'm going to put that in my calculator. Square root 0.38 times 0.62 divided by 1,200. Close it up. Well, actually, I don't even need to close it up here. Just need to make sure it's all under the square root. And I get 0.01401. So that's the standard error. That's the standard deviation of the distribution of sample proportions. Now, what do I want? I want to estimate the probability that 40% or more, well, there's 0.38, there's 38%, so 40%, and since I'm using decimals here, I'm going to change that to 0.40, change that 40% to 0.40. I need that area right there. Now, if this said 40% or less, then I would need this area. But it says 40% or more. So I need that area. Now, how in the world are we going to calculate area under a normal distribution? Well, guys, we're going to do it like we've always done it. We're going to use stack crunch. So what's the mean? 0.38. What's the standard deviation? Square root 0.38 times 0.62 divided by 1,200. We need P what? Greater than or less than? Greater than 0.40. And compute. And the answer is 0.0767. Guys, it's that easy. Now, let's go look at another type of problem. 38% of Americans. Well, getting ahead of myself. Believe in ghosts. Now, guys, I committed a no-no. Remember the conditions. I got ahead of myself here. Let's go back and check the conditions. So before I go on to this next problem, let's check conditions. I was so excited to show you how to do the problem. I lost my mind and went ahead and did it without checking to make sure that the conditions were met so we could even use the normal distribution. First of all, we need independence in random. Well, the randomness was given in the problem because it said estimate the probability. No, I'm sorry, it said a random sample of 1,200 was selected. So, guys, we have randomness. We'll just assume that we have independence. Next thing is we need NP and n times 1 minus p, both to be bigger than 10. Well, guys, the n was 1,200. P was 0.38. Clearly, that's bigger than 10. $456. And we need n times 1 minus p, which we saw earlier was 0.62. Well, we know if 0.38 times that's bigger, this will be too. 816. So both of these are greater than 10, so we can check that box. And the final thing is we need our population to be greater than or equal 10 times our sample. Well, 10 times our sample was 1,200. That's 12,000. Is our population all Americans? Is there more than 12,000 Americans? Yeah, there is. So, guys, the third condition is actually met. Now, let's go on to a similar problem. So, 38% of Americans believe in ghosts. A random sample of 850 Americans is selected. What is the probability that less than, hold on, I want to calculate something here real quick. Less than 300 believes in ghosts. Now, guys, what's the difference in this problem and the one I just worked for you? I made them the same practically for a reason. 38% of ghosts, population's the same, sample size is a little different, 1,200. Over here it's 850. But notice the big difference. The big difference is over here I gave the value that you're going to calculate as a percentage, where here I gave you the value as a count. Big difference. But we know that p hat can be given as what? A percentage, which was given in the last problem, a decimal, or a fraction. And we've got to choose the one that gets us to the decimal. This is the end goal. The last problem, we had 40%. we changed it to a decimal, 0.40. But we don't have percentage this time about the sample. We do about the population, but we don't about the sample. But we know that 300 out of 850 can be changed to a decimal. .3529, which is 35.29%. But the end goal is this right here. So guys, essentially what we've got now is we've got the same distribution. %38 is the mean. And we have 0.3529% right here. And we want less than. So in this class, how do we find area under the curve? We go to StatCrunch. And we put our stuff in. So 0.38, guys, this is going to change. How's it going to change? 0.38 doesn't change. 0.62 doesn't change. But our sample size is no longer 1,200. It's 850. And we don't want greater than, we want less than, and we want to put in the 300 divided by the 850. Guys, if I had $1 for every time somebody just puts in 300 because they get sloppy and they just concentrate on that 300 that was in the problem, I'd have a whole lot of dollars. Compute, the answer is 0.052. All right, gang, that's all I got. I wanted to keep this as I kind of want to use the KISS principle, keep it simple, stupid, right? I wanted to play. I wanted to keep it to the basics, because again, we got kind of limited time this week, and I'm just building a foundation where we can get into the good stuff next week. So, guys, that's all I got. Have a good one.